Can you see my slides?
Yes, I can see.
So today I'd like to share my experience in software development, scientific software development, and it's based on Python mainly. And I will start with explaining why I need to develop scientific software, what scientific software is, and how we do it. And then I will show you example of usage, and all what I'm going to talk today is going to be related to our recently developed software called NanoNet. NanoNet stands for Nanoscale Non-Equilibrium Electron Transport, and the code is available online on GitHub. So why do we want to make scientific software? I mean, there are many reasons. One reason, which is obvious, is we want to make a tool that can be useful for others. So we want to produce something useful for society. Another reason we develop scientific software because we want to disseminate our knowledge. So usual way to spread knowledge is to publish papers or books. But nowadays, software can be considered as another way to spread knowledge because you can publish it and people can use it. So any equations, any theory can be implemented as a software. So it's a modern way to spread knowledge. And many scientific papers, they come together with software. They have references for software packages. Also, developing software is a very nice way to collaborate with other people because the modern software industry has many useful tools for collaboration, and scientists use those tools to collaborate. For example, especially nowadays when we are in lockdown and we need to work from home, we can use GitHub to share codes, to communicate, to work on same things. And also sometimes journals, they ask us to reproduce results. And if you have codes with many parameters set in, you can reproduce results. For example, if you publish a plot in scientific paper, you can provide means how to reproduce this plot using your code. And many papers, especially papers in computer science, in computational physics, in quantum chemistry, they require code to be attached to papers because they want to see how you get these results. And also, if you work in large group, you want to accumulate knowledge in a group where many people are working. Each time someone contributes to the group, we want to keep track of everything that has been done, and we want to have a database of knowledge produced by other people, and software and code base can be considered as a way to accumulate and accommodate knowledge. So what is scientific software? You can consider two layers. First layer is a kernel. Kernel is a part of software which does the job. So computations, equations, everything is implemented in kernel. Another layer of software is interface. Interface means how software interacts with the outer world. So there are different types of interface we can implement. The most basic interface is command line interface. Command line interface can be implemented in a fast way, and it's very economical. And in command line interface, your software produced in text information mostly, and it reads input from standard input stream, and it produces output into standard output stream, and it also can save files in TXT or binary format. And more fancier software, they gives you graphic user interface. Now, in scientific software, we don't really see many graphic user interfaces. They mostly use command line interfaces. Nowadays, it's very popular to build web user interfaces because it's cross-platform, and especially if you want to serve your software performance online in servers, it's good to have web interface, and you can run your software remotely, and you can set up parameters in browser. So sometimes it's useful to have web interface, but in most of cases, command line interfaces are enough because we can we can read out text information and we can process this. And also it's good to have economical interface, because sometimes you run your applications remotely on server, and not always graphic user interface can be compatible with servers. So in case of command line interface, you always can be sure that you can read output because it's standard output. And if you are talking about kernel, we should consider hardware. So it's very important to understand what kind of hardware architecture you are going to use, whether it's going to be multi-processing application, or you are going to use graphic processor units, or maybe you are using MPI function. So depending on which hardware architecture you are using, it will affect kernel architecture as well. I usually follow this workflow when I do software development. First, we need to state the problem. We need to know what we want to achieve, what is the goal, and then the next step is design. This is the most creative part. When we do design, we actually generate algorithm and we develop software architecture. Next step is implementation. Using certain programming language, we implement design developed before. Then we need to verify that our software is actually doing what we want, what is expected. And at the verification step, we produce benchmarking and testing results. After verification, we do deployment. We want our software to be available for other people. We want to share it. So this is what deployment is all about. We push software either to a server or to code base. And then we need to maintain our, we need to update it. We need to fix bugs. And sometimes we need to redevelop it from scratch, and we can loop through this workflow several times. So in the next part, I'm going to go through all these steps and discuss each of them in details. So let's start with problem statement. This software I'm talking about is an implementation of the semi-empirical time-bounding method. This is a method of quantum chemistry which allows you to compute band structure of large systems. For example, here we can see cross-section of a FinFET transistor, and this FinFET transistor channel is 5 nanometer wide. And in this cross-section, we have 833 atoms. So this system is considered to be large because it's very hard to solve this problem using DFT methods. And semi-empirical time-bounding method is a kind of simplified way to get band structure. So let me give you a couple of notes on time-bounding method. So in quantum chemistry, we always have Hamiltonian, stationary Hamiltonian, and we can represent this Hamiltonian in matrix form. So using identity expansion here and complete basis set, we can represent differential operator H into matrix form. In computational physics, everything ends up to be matrix. Everything will be matrix at the end. So we have this Hamiltonian in matrix form. Depending on what type of basis set we use, we can have different forms of this Hamiltonian matrix. In time-bounding method, we use localized orbitals. Localized orbitals means that each atom has a certain set of localized basis function. And in this basis set, Hamiltonian is a sparse matrix because we can neglect interaction of atoms that are far apart. And if we take into account only interaction between nearest neighbors, we have pretty sparse matrix. Comparing to plane waves, if we have plane waves as a basis set, this matrix is very dense. So that's advantage of time-bounding method because it leads to a sparse representation of Hamiltonian because we neglected high order interaction. Because really, nearest neighbors, they interact the most. And each element of this matrix can be factorized into radial dependence, angular dependence, and also we have some phase factor which comes from the periodic boundary conditions. This phase factor is a result of Bloch theorem. And angular dependence is different from different symmetries of atomic orbitals. And in semi-empirical time bonding method, we define what symmetry of orbitals we are going to use to reproduce wave functions. And for some materials, it's just sp orbitals. For other materials, it's d orbitals for metals. So it's all come from quantum chemistry, and we don't need these details for now. You just have to keep in mind that this matrix element has radial, angular dependence, and phase factor. This is how time bonding Hamiltonian matrix looks for graphene. So graphene, it has 2 atoms per unit cells, and that's why we have 2 by 2 matrix. And if we have just nearest neighbor approximation, instead of radial dependence, we have just a constant. And it's known that band structure of graphene consists mostly of p orbitals pi stacked together. And this sum is the sum of 3 nearest neighbors, because each atom has 3 nearest neighbors. Okay, so we see that this matrix is pretty simple. It's just 2 by 2 matrix. But imagine if instead of 2 atoms per unit cell, we have hundreds atoms per unit cell. For example, if we don't have periodic boundary conditions in one of directions, if we have nanoribbon, then we can't use only 2 atoms per unit cells. We have to take, so our unit cells becomes very large if we have nanoribbon or nanotube. And this matrix can be very large. And manually, to compose this matrix manually is a very hard problem. So we need to have a software that can compose Hamiltonian matrix from a list of atomic coordinates. Also, you can see that in nanoribbon, not all atoms have 3 nearest neighbors. These atoms at the edges, they have only 2 nearest neighbors. And we need some kind of processor that can generate this matrix automatically. And this is what our software does. Imagine that we already have this matrix. We can have Hamiltonian matrix in a dense or sparse format. What can we do with it? So 2 obvious things that we can do with matrices are either we have to solve an eigenvalue problem, or we can invert it. So if we solve eigenvalue problem, we will get energy spectrum of our material, band structure, and wave functions. If we invert matrix, we will get Green's functions. Green's function is a kind of response function. It shows how this matrix, how material is responsible for certain external perturbation. And these 2 post-processing can be done in our code. Okay, so now we know what we want to achieve. We want to generate time bonding matrix, and we want to either diagonalize or invert it. So design of our software, it consists of 2 parts. One block is time bonding TB. This block is responsible for generating time bonding matrices. And another block is non-equilibrium Green's function. This is essentially post-processing. So when we have Hamiltonian matrices, we can, as I said, either diagonalize it or invert it. And all this happens in an EGF block. So time bonding block, it has to have input, which is atomic coordinates, and a table of 2 center integrals. If we have these 2 inputs, our time bonding model can generate time bonding matrices. And then we insert these matrices into another module, and we can get physical quantities of interest, which are Green's function, self-energies, and all other stuff. But we shouldn't worry about details. Let's just consider development process, how we develop it. So first we need to develop algorithm. This is algorithm of time bonding module. Okay, it looks pretty strange, and let me just explain it line by line. So the first step, we have to take as an input list of atomic coordinates, and then we need to sort this list. Why do we need sorting? Because depending on the order at which we address each atom, we can get different sparsity patterns. The bandwidth of final matrix is dependent on the order, how we go from atom to atom. For example, if we go in random order, we have very large bandwidths. If we go in this order, we have smaller bandwidths. And there is also optimal order when we get very narrow bandwidths of the matrix. And this is what we want to achieve, because there are many algorithms for inverting matrices which works more efficient when we have small bandwidths. And of course, bandwidth of matrix depends on the structure we consider. So here is an example of rectangular nanowire, and this is minimal possible bandwidth we can achieve, and we can divide this matrix into 3 block diagonal form. And this is all useful for numerical algorithm for inverting matrices. And this is quantum billiard. It has more blocks, and yeah, so our algorithm can find diagonal blocks and off-diagonal blocks. When we sort atomic coordinates and find blocks, we compute offsets. Offsets is essentially indices of orbitals in Hamiltonian matrix. We have to keep in mind that we can have different types of atoms, and each atom can have different number of orbitals. And we need to locate position of orbitals into time-bounding matrices, so we compute offsets. And next step is the most essential one. We have to build KD tree. As I told you, this algorithm, as I told you before, this algorithm is relying on finding nearest neighbors. So we need to find, for each atom, we have to find nearest neighbors to compute non-zero Hamiltonian matrix elements. And KD tree is a data structure that can be used to arrange spatial data into trees to locate nearest neighbors faster. So once we build KD tree, then we can query KD tree, and for each atomic site, KD tree can give us nearest neighbors within certain radius in a fast way. Fast, I mean O logarithm n, where n is the number of atoms. And then we just loop over each atomic site, we find nearest neighbors, we loop over all orbitals for one site, we loop over all orbitals for another site. And if we know atomic site, if we know orbitals, and if we know second site and orbitals at the second site, we can compute matrix element. And this is how we form Hamiltonian matrix. What is good about this algorithm is that we address only non-zero elements. So we can immediately store this matrix in sparse format. So because we don't consider atoms that are far apart. So when we find nearest neighbors, we consider only nearest neighbors, and we don't address atoms that are far away from certain site. Okay, now finally we are getting to interesting part. Let's implement this, how we should implement this. First step is to choose programming languages. Here is the popularity of programming languages. We see that Python is number 1. Then go C, Java, C++, JavaScript, and so on and so forth. I mean, this table means nothing, actually, because popularity is not the criteria which we should follow. We should be reasonable and choose language which suits our purpose the best. And here is the reason why I choose Python. First of all, Python is a language which is easy to use, and it's fast to develop. In big companies, Python usually used for prototyping. When we have an idea and we want to implement this idea fast, we use Python. And then if it works, we can do improvement and we can transfer codes to C++ and other languages we want. Another advantage of Python, it has very economical syntax, and it's very good to create interfaces and API, application programming interfaces. It has very nice syntax, very economical. And I see that the same trend is followed by C++ as well. If you take a look on recent versions of C++, starting from C++ 11, we see that they implemented new data types. For example, auto. This data type is a way how compiler guess your data type automatically for you. So you don't need to know which data type for variable you use. And this is how it works in Python. Python also doesn't require you specifying data type. It tries to guess what you want based on your data which you provide for variable. And I was amazed to see that in C++20 they implemented import. Import is a way how Python can be extended, how Python use modules. And instead of include statement, in the latest version, C++ provides you import statement, which works very similar to Python. So we see that C is trying to get more high-level language, and it tries to put more responsibility to compiler to do some work for you. So user don't need to take care of types and all other details. And also Python has many useful built-in data structures and algorithms like linked list and trees and searching algorithm. And it's also true for C++. C++ has many template libraries which do the same things. And Python can be linked to other languages. So if you have code written in Fortran on C or C++, you can run this code within Python very easily. So you can use Python just for interface, for making interface. Of course, if you write everything in Python, your code may be slow, and Python has problem with threading because it has thread lock, and it consumes lots of memory because it does job to recognize what data types you use, and it do many computations for you in the background. But yeah, this can be overcome in a way. And another reason why I use Python, because it has already many numerical libraries, NumPy, SciPy, and nice library for visualization. And these libraries are very fast because NumPy, for example, it's written in Fortran, and Python just provides you interface. NumPy is essentially LAPACK library, and SciPy, many codes are written in C++ and Fortran, and SciPy provides you with the Python interface to those low-level codes. So having those libraries is very useful. Next thing I'd like to talk with you is DevOps. DevOps is a very important part of software development. It provides you many tools that simplifies your life as a developer. So DevOps it's practices and tools that can organize you and your developing process, and it provides you services which can speed up your developing processes. So it's all about efficiency. If you use DevOps, your software development becomes faster. Let's go through some of them. So first one is joint development. It's very rare when you work on your codes alone. Usually you work with your colleagues, partners, and you want to share codes with them, and you want to work on the same code together. And working together should be, in principle, speed up development process and should lead to better quality codes. And to do joint development, we need to use version control system. I use Git, and version control means that if you make some changes in your codes, you should register these changes, you should commit, and system will keep track of all your changes. And if somebody else contribute to your code, he can make another version of code, and you can switch between different versions, different branches. And also, if you have GitHub account, you can push your code online, and you can share your code, and you can work remotely on your codes. So this is my GitHub account for this project. And yeah, you can see there is all files available, and there is link. You can clone this, and everyone can access this code, and I can share it with my colleagues. And there is also many useful things. We can discuss this code, we can annotate it, comment it, and other stuff. Another important DevOps which we should consider is continuous integration. Continuous integration is about ability for everyone to continuously change your codes. So if I want to add a patch, I can do it at any time. If someone else wants to modify my code, add some patches, they can do it anytime they want. But of course, system should take care of it, and it should be done in a reasonable way, because I don't want anyone to break my code. And this is what continuous integration is all about. So if someone wants to make changes in my code, it's gonna be in a safe way. There are many continuous integration systems. GitHub has embedded continuous integration line. There is very nice GitLab server, which is very popular for scientists. There are many codes on GitLab. I'm using Travis continuous integration server. So continuous integration is very simple to implement. You can link your GitHub account to any of continuous integration services, and then you need to provide configurational file in your code base. This is my configuration file. So the first part just say on the server you should emulate Linux operational system. Then I describe what requirements is for my software. So those software has to be installed before I run my Python package. And then the most important part is scripts. Scripts is something that has to be run in order to make build successfully. So if scripts failed to run, there is an error reported, and this build is considered as unsuccessful. If those scripts run successfully, then builds gets green light and everything's fine. And it's up to you to set up any scripts you want. So you can set up what do you consider as a successful build. In my case, I run nose test. Nose test is a script that collects all tests in my project and runs them. And if all tests are successful, then build is considered as a successful. And also I run PyLint, which checks errors, syntax errors in Python codes. So the condition that my build is successful is that all tests run successfully and there is no syntax errors in my Python code. Then you specify on which branches you want to run those scripts. For me, it's just master branch. And also you can do some post-processing job. After everything runs successfully, I want also to estimate what coverage of my codes for test. So coveralls is a script that computes how many lines of codes are covered by tests. And yeah, also you can run here some statistics. You can run here code quality tests to estimate how good quality of your codes, but this doesn't affect your build. So the most essential part is scripts. If scripts run without errors, the build is considered as a successful. You can run your application with certain parameters here and do whatever you want. And successful build is a condition that patch or code can be added to your project. If some user add a piece of code to your project and scripts failed with this piece, this patch cannot go through. It will be rejected. That's the essence of continuous integration. It gives you conditions what to be considered as a good patch, good code to be added to your project. So yeah, and this is a web page from continuous integration Travis for my project, and it shows the last successful build, how much time does it take to run it, and all the steps that has been described in configurational file are shown here. And also it shows history of all your builds. Green means that build was successful, and if build failed, it shows red light here. Very essential part of making good software is documenting. You should write documentation. and it can be very tedious, but good way to start is to write README file. Usually README file is written in markup language. That's why you have extension MD here. And this is example of README file. In README file, you basically describe what is your project about and how to install it, what is requirements for your project. Another aspect of writing documentation is writing docstrings. Docstring is a Python way to write comments in functions and modules. Here is example of docstring. So let's say I have functions that called cut into blocks. And at the beginning of each function, you need to write a line of comments describing what this function does. Then you describe input parameters, and you describe output parameters and data types of parameters. And you have to write, in principle, you have to write docstrings for each function, each module, each class, and everything should be documented. Why? If you have it, you can use Sphinx. Sphinx is a web server, which when you install Sphinx, you can run it for your codes. And when you run it, it collects all docstrings for all your files, and it makes one single PDF file describing functionality of your codes. And you can also add your README file on top of it, and you can add additional files written in markup language. And Sphinx will collect and compile all your documentational files spread over all your Python scripts and other files, and it will make one single solid documentation. And Sphinx can output documentation in different formats. It can make LaTeX file, PDF file. Also, it can make HTML file, so you can put your documentation on server. And yeah, it's a very useful tool, and I highly recommend it. But if you want Sphinx to produce reasonable documentation, you need to write comments everywhere. So Sphinx can recognize your comments, and it can extract this notation from your docstrings. So there are different formats for docstrings, NumPy format and Google format. So Sphinx can recognize all of them, and you can follow any convention for docstrings you want. So Sphinx is a Python documentation generator, and it's very useful, and it can save you time writing detailed documentation for your project. In the continuous integration, we saw that as a measure of success, we write tests. So continuous integration is considered to make successful build when tests run successfully. So the testing is a very crucial part of developing software. That's why we have to write lots of tests. There are different types of tests. Unit tests is a test of very simple single piece of codes. Functional tests, it's a test for bigger bunch of codes, and usually you provide some input arguments. You run part of your software and you check whether you get expected output. And also you can run performance tests. If you want your project to work within certain margin in terms of CPU time, memory consumption, you can make performance tests and check that your updates doesn't break them. So if you want to keep your project to be of good quality with good performance. Here's an example of functional test. So in my project, I made a directory called tests. And in this directory, I just create a bunch of Python scripts with lots of functions, and each function starts with word test. And then you just give a name what you want to test. I want to test how my code is operating for single atomic chain. It's very challenging to develop good tests. So there are certain requirements for tests functions. Tests should be run fast. You don't want tests that take 1 hour to run. So you should find out simplified system, simple enough to compute fast. But also this test should cover lots of codes. So in principle, in perfect world, your test should cover each line of code. All codes should be covered by tests. This is perfect ideal world. And here I created atomic chain, and then I compute band structure, and it all doesn't matter for you. The only thing that is important here is the last line 26. At the last line, I compare band structure that I obtained using my code with analytical value. So in this particular case, I can compute band structure analytically, just cosine function. And I compare two arrays. One array I obtained using my code, another array I obtained using analytical method. And I compare these two arrays element-wise with certain precision. And if they are close enough, then this test is successful. So a NumPy library has testing module which can compare arrays with different precision. If these arrays values of elements of these arrays are far away, then this test will fail. Okay. Another way to run tests in Python is to embed tests in docstrings. So this is a previous example. I've taken it from documenting part, and we can continue writing this docstring and add some tests. In docstrings, everything that starts with this arrow will be executed, and then you can write lines what you expect to get. So for example, this line outputs matrix H0, and below you type what you expect. I expect this matrix to be 1, 1, 1, 1, 1, 1. And then when you run test, if this matrix H coincides with what you expect, then test is considered as a successful. If this matrix is different, the test will fail. Okay. And yeah, lots of testing techniques, lots of ways, but there is one tool for all, which is nose. Nose is a Python script that goes through all your codes and it collects all your tests and runs them. So for example, if you nose test consider Python script to be a test if its name, its file title starts with word test, like here. So if he sees files or functions that start with word test, it says, okay, it's test, I'm gonna run it. Also, if you add a parameter with doc test, it's also going to dig into your Python files and collect all doc tests and run them too. So at the end of the day, you will get all tests run, and at the end you will get report how many tests has succeeded, how many tests has failed. And nose test will throw exception if at least one test has failed. So it's very useful to run this function on the server with continuous integration, because if all tests are successful, it goes silent. But if at least one test failed, it throws exception and everything breaks and your code cannot go through. So this is to collect and run all the tests. And I use this script into continuous integration pipeline here. Nose test with coverage. I also want to compute coverage, how many tests cover in my code. All right, so this is all about testing. Deployment. So imagine that everything works as expected. You've developed your package and everything is fine. Now we have to distribute package and make it accessible for users. And the first step is to make a package. And making package in Python is all about setup.py script. So you need to create special Python script called setup.py, and this script creates object setup, and you need to set up all the parameters for your project. You need to specify name of your project, version, title, authors, and also you need to specify dependencies here and requirements. And when your setup file is ready, then you can create packages. You can, if you have setup file, you can just install your project for your operational system, running pip install dot. Dot means current directory. I assume that we are in our project directory, and when we run pip install dot, it means install current project in this directory into operational system. Or you can make source distribution package, Python setup.py, as dist means source distribution, and then you can specify which format you want. It can create zip archive or any tar archive, any archive you want. Or you can make build distribution. Build distribution is more like binary files. For example, for Linux, you can make RPM package for your Python software. And all these steps require setup file. So to make package, you need to describe all these details for your project. Now, when we have packages, we can deploy them on server. So one obvious way to do is just to use GitHub. So if you have your project on GitHub, you can consider it as already deployed because you can share a link to GitHub, and any user having this link can clone your project. Then they can enter project directory. Then they can install all the requirements described in the txt file here, requirements txt, and then user can install your package and test it, and that's it. This is one way to deploy Python project. More general way is to use PyPy. PyPy is a collection of all famous Python Python packages such as NumPy, SciPy, Matplotlib, and others. And if you want, you can register your project on PyPy. If you register it here, people can access it just using this simple command. Of course, if they have internet, then they just can type pip install nanonet, and what it does, your pip goes to PyPy, and it tries to download it from here. And here is PyPy page for nanonet for our project. And yeah, the process of deploying project to PyPy is very simple. You just need to set up certain scripts. You just need one software which is called Twine, I guess. And you need to create account here. If you have account and you have set up all configurational files, you are good to go. So this is another way to deploy a Python project. And if you do it, you can just give name of your project and everyone can install it using pip install. All right. At the end, I have this directory tree for my project, and I think I can show you how it looks in real life. So this is my GitHub account. This is my directory tree. Let me zoom it up. I have a directory called nanonet. This is where my Python files are. Also, I have tests. This is directory where all my tests Python scripts are. So you see they start with what? Test, test, test. Also, I have a directory with examples, just to show how to use examples. And it's for Python, it's also useful to make Jupyter notebooks. Jupyter notebooks is an interactive way to show how to use Python projects. You can open it and you can see piece of code with outputs and with visualization, and you can create many Jupyter notebooks for different cases to show how to use software for different circumstances. And there is directory for documentations created by Sphinx. And here is some configuration file. README file on GitHub. README file is output here on the web page. So this is content of README file. Also, you have configurational file for Travis continuous integration, as I shown you before. Yeah. And here you have statistic, how many people downloaded your code, dependencies graph. So yeah, git clones, visitors. And here branches from your virtual control. So on this project, I worked in a group with approximately 5 people. And on GitHub, each guy made own branch and contributes to own branch. And then there is also main branch called master. And if we consider that this feature is working well, we can merge branch to main branch master. And master is what is used for production. Okay, let me go back to my slides. So at the end, I plan to show you how my software works. So the interface is essentially API functions. So this NanoNet package provides additional Python functions that can be used with other function code to do computations for atomic structures. For example, you can import NanoNet using import statement, import nanonet.typebinding. I use shorter name typebinding, and then this typebinding module provides you with many classes which helps you to create orbitals, set up typebinding parameters, and you have to define atomic coordinates. And then the most important object is Hamiltonian. To create Hamiltonian object, you need to specify atomic coordinates, you need to specify nearest neighbor distances, and you can specify whether you use orthogonal localized atomic orbitals or non-orthogonal. If you are using non-orthogonal, you need to compute overlap between them. And then you just use proper Python syntax. You create matrices, you compute band structure. Band structure is computed by diagonalizing this Hamiltonian object. And at the end, you can visualize your data using matplotlib. So when you install NanoNet, you can use additional Python API functions to do electronic structure computations. If you want more information, of course, you can read some books. For example, I like this one, this particular book, Writing Scientific Software. And yeah, it's a good style book. But I think more useful would be to just read source codes. There are many successful scientific applications and software developed. For example, Quantum Espresso. It's written in Fortran, but it has all this feature I've discussed before. It has continuous integration. It has GitHub account. It has good tests, good testing routines. And if you just dig into source codes, you can learn a lot. That's my way. This is how I learned how to write scientific software. I'd like to thank my team. It's a pretty big group of people, but about 5 people from this photo works on NanoNet. My supervisor, Jared Cole. And also I'd like to thank National Computational Infrastructure of Australia and Australian Research Council for supporting this project. Thank you very much. And if you have any questions, I would be very glad to answer them.
Thank you very much. Any questions? Turn on your microphone.
Yeah, thank you very much. Very interesting talk, Mykhailo. I was really enjoying your speech. Well, particularly because I am familiar with some of quantum physics, so I understand for lots of students that are just interested in software development or not familiar with quantum physics, probably lost a bit of context. I mean, in physics way, but I'd like to make some questions on development process. When you work with a team, with development team, do you use some development techniques like Scrum, Waterfall, or whatever?
Yeah, we were thinking about to implement it. So yeah, one important part of software development that is missing in my talk is project management. And if you work with large group of people, you have to distribute tasks and you have to be sure that everyone perform well and everything is delivered in time. And for that, we have software development community have several techniques like Scrum, Agile, and no, we don't really use them because we're a pretty young team. We just started developing this project about a year ago, and we are a small team. So in terms of project management, we just have weekly meetings and we discuss what has to be done. And we have only 5 people and everyone is working on very isolated problems. So we do not overlap much. And my performance in this project doesn't depend much on performance of other people because I'm working on one theory and they're working on another. For example, I'm responsible for generating tie-bonding matrices. Other people are responsible for non-equilibrium Green's functions, and we do not overlap much because they need they need matrices for Green's functions, but they can use some dummy matrices, simplified matrices, and they don't really depend on particular form of this matrix. But in future, yeah, if we grow up, if we decide to implement more features, then we need to implement project management styles, especially if we hire more people, then it's very crucial. But in this particular project, we didn't do smart way of project management. It was pretty ongoing and random.
Okay, thank you very much. Related to this, I have another little question. I know you worked in Samsung for a year and a half.
Yeah.
Yeah. So, how the development in Samsung differs from development in the university, in the institution?
The difference is huge. I mean, industry works in pretty different ways. I mean, everything is large scale. If you work in industry, you have more people working on the problem. You are more dependent. In academia, you're more independent. You work entirely yourself on big part of project. And in industry, you work on a small piece of code. And sometimes several people work on a very small piece of code. And yeah, it's very hard to say where responsibility is higher. And in company, we use lots of project management. We use Scrum. And we had special guy who was responsible for distributing tasks and he was implementing project management techniques. But in general, it's pretty same. I mean, if it comes to software development, in this sense, it's same. I mean, we did programming. In academia, I also do programming. We use same programming languages, and this continuous integration stuff is pretty same. And if you take a look on professional teams in scientific software development, they also use pretty advanced techniques similar to what industry is using. So.
Okay, thank you very much. And
I mean, it's similar to conclude. Working on software development in academia is similar to industry, but it's smaller scale. So that's the only difference I consider.
Thank you. Another question about deployment process. Do they really allow anyone to upload to PyPy? So you just create an account and you have your software and I don't know, it may be ugly, it may not work, but you can upload it to PyPy?
I guess so. They have several requirements, but those requirements are very basic. I mean, the only requirements I think I needed to have is to have README file, to have license file, and I'm not sure if they use some continuous integration. I think even if your code is failing, you still can upload it to PyPy. So it was pretty straightforward for me. They allow you to do it in two ways. You can create dummy account just to practice to see how you set everything up. It was pretty tedious to set everything up. You need to specify a version, you need to specify description of your project. It's simpler if you have already a GitHub account. So you just give links and engine on PyPy is trying to retrieve all the information from GitHub. But in terms of performance, I don't remember they had any special requirements. I think even if you have very crappy software, you can still upload it.
Okay, that's interesting.
But I have to recall, because it was a year ago. I mean, once you created account and uploaded first version, each next version doesn't need anything from you. You just do it automatically. You can even integrate deployment to PyPy into your continuous integration pipeline. And each time you add a patch of code, it goes to PyPy as well. You can do it. So I don't remember because it was a long time ago when I created first account for NanoNet. But I don't remember any struggles there.
Yeah, it's another question. How long did you develop this NanoNet? How long did it take? Because we can see that the code is actually very well developed. It's very advanced, and it has a part of
about a year. Yeah, I started about a year ago.
A year.
Mm-hmm.
Okay. And the last one, just personal interest. Why Python? Why can't you use like MATLAB? It's easier for prototyping and everything.
MATLAB is commercial software. I don't want to pay money. And nowadays, Python offers you same functionality. I mean, I don't know any aspect of programming that MATLAB can offer that Python can't. All what I can do in MATLAB, I can do it in Python using NumPy and CPy. And since it's open source and community is free, I would rather use Python for this reason.
Okay, thank you very much.
You're welcome.
That's all.
Any other questions?
Another question?
Yep.
No? Okay. Thank you very much, Doctor.
Thank you.
Thank you. Thank you for your participation. See you later. Thank you.
Have a good day. Goodbye.
Have a nice day. Thank you.
Thank you. Bye.
Chicos, les pasé en el chat la